A couple of reminders before that. Don't forget about the leftover tickets that you will be able to pick up from the Red Hat HR person in near the exposition center. You can pick them up at 1440. So go there to pick the leftover tickets. Please don't forget after the presentation, this one and all the others, to leave a feedback. You can see the URL on the whiteboard. Please complete the feedback so the presenters know how well they did. Some of them will get some prizes at the end. And may I introduce Florian with a presentation about a very cool package, which is nftables, the future of IPtables.
So welcome everyone. The talk is the agenda of the talk will be roughly. I will first explain what nftables is and why it's being created. Then we will have a look at some of the underlying features in the kernel that nftables is using, so that we are on the same page with regards to some of the terms. Then we will talk about the limitations that IPtables has, and then we will look at how nftables avoids these and solves some of the underlying problems. And then there will be a couple of examples of things that you can do with nftables that you can't do with IPtables. So nftables simply is a new packet classification framework based on lessons learned from IPtables. It was first presented publicly at the Netfilter workshop in Paris in 2008, and then finally merged into the kernel roughly 2 years ago in 2014 for 3.13. So what's being replaced? Most simply speaking, IPtables, IP6 tables, ARP tables, and EB tables. The latter one, which is the bridge filtering framework. So all these Userspace tools go away and they are replaced with a new one. And at the same time, we are also replacing the kernel implementations that does the IPtables, IP6 tables, and so forth, runtime evaluation of the rule set in the kernel. What we do not replace is the connection tracking engine, network address translation engine. That stays the same, and we are also reusing the existing Netfilter hooks. We will look at what that is. And the Userspace packages like contract tools, contract daemon, and ulogd for packet logging also remains unchanged. So we are not replacing everything. It's just basically the IPtables and IP6 tables and so on. Now the more interesting question is why? Because you usually do not replace something that just works, and IPtables works pretty well. But it does have some fundamental problems in its architecture that are not resolvable without changing so much that basically a rewrite is the only way to do it. One problem with IPtables is there was just IPtables, and it did only do IPv4 filtering. And when IPv6 stack was added, what happened? Basically IPtables was copied from IPv4 Netfilter to IPv6 Netfilter, and then someone replaced all the IPv4 addresses in the code with IPv6 addresses, and then you had the same code base twice. And the same happened again with Bridge and with ARP, and so basically we have the same code 4 times in the kernel with slight variances for the different protocol families. At the same time, we have very similar extensions that basically just do the same thing for different protocols like TCP or SCTP, and it's getting out of hand. And at the same time, Userspace has all these different tools, so you have to, if you have to do bridge filtering, you can't use IPtables, you have to use EBtables, and the greatness is it also has slightly different syntax than IPtables, which is greatly confusing. And people that want to use IPtables in a programmatic fashion also basically lose on every scale, because there is no way to do it trace-free and to learn what rules exist. So it's basically a mess, and there's no library that you can use for IPtables. There is libiptc, but that's an internal library for IPtables, and it does not have an exported stable API. So basically, if you use that, then you are on your own anyway, and there's no support whatsoever. So what are Netfilter hooks? I mentioned that briefly. So basically, if you look at the kernel source code and grab through that, don't worry, there will be not much C code in this presentation, so calm down. You will see a bunch of inline functions or macros called nf_hook that are sprinkled across the kernel and placed in strategic places. And basically all this does is it provides other kernel modules a point where they can register functions that will then be called by the kernel for a packet. And these functions then have control over what to do with the packet, like drop the packet, move on to the next hook, or queue it to Userspace, things like that. And all the Netfilter features, like IPtables, connection tracking, and so forth, use these NF hooks. So they register with the kernel something like, I want to see packets that arrive that come in, and please call this function when that happens. There are 5 of these hooks in the IP stack, then another 5 in the IPv6 stack, similar for the bridge. And if you look at the hook names, you have used IPtables before, then you will instantly recognize those names because they are also matched with the built-in chains that IPtables offers. So for instance, IPtables filter. Yes?
We can say maybe go non-full screen. Or just adjust the resolution.
No, sorry. Sorry.
Can you add a second monitor?
I don't have a second output device here. Sorry. No, sorry. My bad. But unfortunately, there is not much missing from the slide. Because the only thing that you can't see is basically the last 2 letters of post routing.
Okay.
There is nothing else on the right side. So the basic idea is that you place these hooks in places where you want to have particular properties. So for instance, if you want to do network address translation and redirect packets to the local machine, you have to change the IP address. And if you change that after the routing decision has taken place, then it doesn't do what you want, so you have to do this before the routing happens. So that's why there's the hook in pre-routing before the routing decision. Then you might want to have different filtering for packets that are being forwarded and for packets that are arriving to the local machine. So that's why you have different hooks for forwarding and for input and so on. Now for IPtables. IPtables, example rule, and things that come to mind here is IPtables limitation. You can only have one target. That's the thing that is after the J. So if you accept in this example, but at the same time you would want to log or to mark, you can't do that in one rule, and you have to copy the rule, or you need a helper chain or whatever. Rules are always stored in a binary blob in the kernel. So what IPtables actually only does, it translates a textual representation into a binary one. It has no idea what it's actually doing. The only thing that the user space knows about is how to parse the text and how to translate that into a binary representation. It has no idea what TCP is or what a port is. It only does the translation. Furthermore, if you run this command and to add a rule, then it doesn't add a rule, but what it actually does, it first fetches the entire existing rule set from the kernel to fetch this huge array of structures. And it mangles that somehow to add this rule into the blob, and then it commits everything back to the kernel. In other words, when 2 persons or 2 programs at the same time try to add rules, then one of the adds will fail and silently disappear because of this race condition. Because IPtables does not guarantee atomicity for individual rules, only for the switching of tables. And that's something that you can't resolve in IPtables because that's just basically how it works. The kernel has no idea what changed in the rule set because it only sees old blob versus new blob. And so it can't really tell you what has changed, and that would also be a desirable feature so that you could, for instance, monitor what rules are being added or removed, but it's not possible to do that. And Userspace has no idea what the rule set is actually doing, so you can't do optimizations in Userspace on the rule set unless you would go the full way and basically duplicate the kernel part that does the evaluation of the rule set in Userspace. So in Userspace you can't do things like eliminate dead rules, you can't detect things like here I could rearrange these rules to make it match faster or things like that because Userspace doesn't know what the rules do. At the same time, we have a linear evaluation of the rule set. So in IPtables, it starts at the top and then one rule after another is evaluated until a final decision is made like drop or accept. We have 4 times code duplication, as already mentioned, for all the families that we support. IPtables hasn't seen any extension since it was added, and it's basically IPtables from 2001, and we still have a reader-writer lock in the main traverser. In other words, it does show up when you profile bridge traffic, and this is really becoming a problem, and it has to be fixed some way. IPtables limitations are being worked around by adding various matches. So for instance, because you can't test for 2 different ports in a single rule with IPtables, someone added a multi-port match, and then you can give it up to 8 ports or 9 ports, I'm not sure, in a single rule. And if you need more than that, you have to add again 2 rules. There is IPset, which is an external tool that you can use to efficiently match on white or blacklists. So you can use the IPset tool to generate a list of addresses or a map of addresses, and then use the IPtables IPset match to directly decide whether it's a hit match or a non-match to avoid IPtables chains with tens of thousands of rules, which you would have to do otherwise. There's the BPF match and the U32 match to match on packets where IPtables doesn't have an existing match. So for instance, if you want to match on, for instance, DNS packets, that's the only way to do it. You have to use the BPF match or something like that. We have a lot of duplicate functionality. So for instance, someone wanted to add the ability to match on IPcomp packets. And what did they have to do? They had to copy the authentication header match and then replace it so that it would work for IPcomp. There are some ridiculous matches for special cases. For instance, someone needed to do load balancing for policy routing and they didn't want to add 100 mark rules, so they added this hash mark target, which computes a hash over the packet and then sets the mark based on that hash. And that's a special feature that not many people need, and IPtables should have offered a generic way to do that without having to add all those special case features. Then we have magic tables, for instance. The Mangle table is special in a way that if during output the mark changes, then it will do a rerouting. But that's something you just have to know because the kernel does it behind your back. So what does nftables do differently? A lot, it turns out. So first difference is all the protocol details are in Userspace, not in the kernel. The kernel, it's exactly the other way around. The kernel has no idea what TCP is. Userspace knows what TCP is, and Userspace knows where in a packet the TCP ports are located and things like that. The kernel is just dumb, and it's just basically, for lack of a better term, a virtual machine that offers registers and then operations that work with these registers. So the nftables tool generates codes or instructions to do what the user has specified, and the kernel will just dumbly follow those instructions without knowing what's actually being tested. So the kernel has no idea that, for instance, the TCP destination port is being tested or the TCP flags or whatever. It just follows instructions like look at this register and check if it's this number and things like that. The main focus of nftables is about efficient rule representation. So you can express a lot with nftables that you can't do with IPtables. We will see in examples what that exactly means. So we replace the kernel implementation of the IPtables evaluation of filter rules, and we change all the Userspace tools go away, and there's a single program called nft, which handles everything. And nft is also at the same time IPtables save, IPtables restore, IPtables and so forth. You can give it a file and it will load all the rules in a file. You can start it in interactive mode, and then you have a shell-like prompt where you can input rules directly, and you can also add rules on the command line. From a kernel point of view, there are no matches or targets anymore, because that distinction is something IPtable specific and it doesn't make a whole lot of sense. So the term match and target has no meaning anymore, and it's just called expression. And an expression can be terminal, like accept, or it can be non-terminal, like for instance log. So you can have as many actions as you want in the same rule, as long as those are not terminal. So you can't accept and drop at the same time, because, well, that's not possible. So we basically have two groups. We have some basic expressions, like immediate, which is just numbers. We have expressions like payload, which basically just asks the kernel to load some bytes from a particular offset and stuff it into a register. Then we have expressions that work with those registers, like is it equal to, is it larger than, less than, not equal. We have bit operations, so you can do flag tests. Counter is also no longer built in. So if you want packets to increment a byte and packet counter, you also have to say, you have to specify this counter expression on the command line. There are a bunch of special and more complex expressions, such as concheck, which is the same as the concheck match in IPtables, so you can check if a packet matches an existing connection or not, or if it's related and things like that. And there is the meta expression, which basically replaces a whole lot of IPtables matches, like mark, for instance, or you can use it to fetch the input interface name and test for that, and everything basically that is somehow not related to the content of the packet itself, but somehow to the metadata associated with the packet, like the firewall mark, the input interface, the output interface that is being used, even the processor ID that is currently used to process this packet. The Userspace frontend has a new grammar, which is somewhat similar to what TCP-dump uses. Userspace parses this grammar and then translates that into the IPtable or the nftables instruction set. Another thing that is very different from IPtables is that the Userspace and the kernel representation of the rules are completely distinct. In IPtables, it's the Userspace and the kernel use the same format, so you can't make changes without breaking everything. And in nftables, the kernel has a completely different understanding of what a rule looks like, which greatly helps with optimization. We have netlink as an intermediate format, and Userspace will just serialize that in this format, and the kernel will just do some sanity checking on that, just to see that, for instance, you don't have infinite loops in your rule set, but it doesn't do anything other than basic sanity checking, and will just translate that to its internal representation. So if you look at this rule there, and you fire up nftables in a debug mode, and it will output the instructions that it has generated based on the input. So for instance, this here, 22, is this number here, because that's the network byte order representation of the number 22. And we see it has generated a payload instruction to fetch from the transport header something, and it stuffs it into register 1, and it does a compare, and if that succeeds, it will place the verdict accept into the verdict register 0. And what it also did, it prepended another payload instruction beforehand, because you're asking for TCP port 22, not for instance for UDP or something else. So it automatically generates this dependency instruction to fetch the protocol header from the IP header, takes that into register, and 6, that's TCP. So it will check if it's TCP, then proceed, and otherwise it doesn't match and it will leave here. Any questions so far? Yes?
I have a question on the last slide before this one. There was about the interface and the meta tags interface, input interface, output interface. Now I'm able to match the interface like HDA, EDH+, so I can match several interfaces. But unfortunately nowadays the system changes the interfaces names, so it's almost not possible anymore. Will this implement this feature so I can match multiple different names of interfaces?
So the question was whether you can match multiple interface names with the input interface names meta match, and the answer is yes. We will see in some examples how that works, because it's not just limited to interface names. It's basically you can match a lot of things at the same time with nftables in a single rule. We will see that in a couple of next slides. The other thing that is different than in IPtables with regard to interface naming is that there are two types of interface naming matches. The one that actually checks for the name, and there's also another one that internally checks for the interface number, so that, for instance, when systemd or something else renames the interface, then it will still continue to match if you use the one form, which matches on the index, because the index is unique and stays the same all the time. Or if you use the other form, then it will no longer match.
Indexes of the interfaces can change.
No.
Yes.
An interface index is always unique.
Between reboots it can change.
Yes, exactly. Between reboots it can change, yes, but it does not change while the system is running, which this was about. So if you
Systemd can change names during boots, I think, not during.
okay, I don't know what systemd does or doesn't do. So yes, this is basically the most confusing feature for people that are used to IPtables, because in nftables there are no tables. Well, that's not exactly true. There are no built-in tables. So what nftables does, it ships by default a few template files, conveniently named something like IPfilter or IP6 filter. And this here is basically how do I get the IPtables filter table in nftables. And what you have to do is you have to say, I want a new table, and the table should be called filter. It could be any name. And in the IP stack, not for instance in the bridge or in the IPv6 stack. And this table is basically just a container for chains. And then you create chains here. And this tells nftables that it should tell the kernel where to hook it up. So you want a hook at input with a particular priority, and you want a hook in forward, and you want a hook in output. So for instance, if you don't want, or if you don't need output filtering, then you could just remove this chain output, and it would also help a bit with performance, because the kernel would just skip the nf output hook completely in the kernel, instead of just redirecting it to an empty chain that doesn't do anything. Same for a manual table. There is also something interesting here. There is no hidden magic anymore with tables or chains. you have to specify a particular type if you want magic behavior. So for instance, to replicate mangles or IPtables mangle output behavior to do a rerouting when packet mark has changed, then you have to tell the kernel that it needs to do some extra work when evaluating this chain. This here is an arbitrary example. So first is the family that you want to hook. The name can be anything that you want. Chain name can be anything that you want. The filter type means basically just the default. I want to accept or drop and nothing else. Route means I want want nftables to reconsole the routing table after it's done. And this here is important to specify which one of the 5 built-in hooks that you want your packets to be hijacked at. This is a family overview. So basically for ARP tables you would use table ARP, for IPtables you would use table bridge, and so forth. There are 2 new tables or new families I should say, in nftables, which is inet and netdev, but we will look at those soon. Other important changes in nftables are finally the rule replacement is atomic, so if several instances try to inject rules at the same time and it succeeds, then the rule will exist in the kernel, and that's it, because all the rule replacement is transaction based. There's a unified tool, so same syntax regardless of what family you are using. So if you use bridge, then you don't have to get accustomed to a different syntax as with IPtables, IPtables. It's just the same. The inet family, which is new, should help greatly with hosts that use both IPv4 and IPv6, because you no longer have to duplicate all your rules for IPtables and IPv6 tables. So if you want to accept, say, SSH inbound, you just accept TCP dport 22 in the inet family, and it will just work for both IPv4 and IPv6. Also greatly sought after feature is the ingress hook in the new netdev family, which allows you to filter packets before they enter the IP or IPv6 stack. So you can actually filter on raw IP sockets. So if you want to say drop raw IP frames, then you can do that in the ingress hook. And it's also different in that it allows you to attach rules directly to an interface. Syntax is pretty much exactly the same as early one. You ask for netdev family, name doesn't matter. The hook name is ingress, and you have to specify a device where the rules should be attached to. And after that you can use the standard nftable syntax to, for instance, check for a particular Ethernet type, and it will generate the required dependencies to make sure that, for instance, if the device is something other than either, then this will not cause false positives.
Sorry, the new ingress, is that before or after IPsec encryption?
It's both, because for IPsec there is IPsec packets travel the rule set twice. So you would see once you would see the IPsec raw frame, and then on the second invocation you should see it on unencrypted.
Just regarding the inet family, I understand the concept regarding the ports, but what happens if you pass IP addresses to that family?
That's quite simple. In the background, if you say IP source address 1234, then it will inject a dependency that guarantees that this rule is only consulted if it's an IP packet. So it will just work. You can use IPv6 or IP addresses in the inet family, it's no problem. Now for some of the more interesting features that nftables has. I already mentioned that it integrates sets. What that means is that you can, in a single rule, use curly brace syntax like this, and then you can give it a list of as many addresses as you want. And unlike IPtables, it will not expand into multiple rules. but if you look at what it actually does, it will fetch the source address in this case, push it into register, and then there's a single lookup instruction that checks whether the address is part of this anonymous map. And based on that, it will just match or not match. Yes?
Is it possible to define a range?
Yes, it's also, the question was whether it's possible to define a range, and yes, nftables also allows you to match on ranges natively without extensions. Another feature is that you can concatenate keys, so you can match on address and destination port pairs at the same time. So that's with this. This means it's basically it's a placeholder, and that it should expect destination address and port as the content of the set. Yes.
Can I mix IPv4 and IPv6 in one set?
The question was whether you can mix IPv4 and IPv6 in one set, and the answer is no, not yet. Another feature is named sets, and for named sets, you can basically reference to the set in the rule set by a name. So you first have to define a name and tell it you want a new set. Then you have to specify what type is going to be used, for instance IPv4 in this case, and a port number. And then you can use the add followed by the name, so add foo here, to reference to this set in rules, so you can use the set multiple times in the same table. And you can also remove and add entries to that set at any time, which should be useful for something like fail to ban. Yes?
Is there support in shortcomings for nftables?
The question was whether if there is support for nftables in Shortwall, and I have no idea. Sorry.
Why would you want to use Shortwall if you already have a tool that is like where you can already write rules I think it's easier to use Shortwall and generate rules for zones or, for example, data centers or subnets.
Could you please resolve this discussion later, because I'm running out of time and I would like to present all the features. Thank you. Since it's cumbersome to remember all those names, you can query the nftables tool to tell you what it is. So if you say nft describe and then say something like TCP deport, and it will tell you inet service, and same for IPv6 or for meta marks and things like that. Next cool features are maps. So for instance, if you want to do a lot of net transformations, you no longer need a rule for every transformation. You can put all of them in a single one with map keyword. So this is basically the address that you are expecting in the packet, and that's the address that you want to replace it with. And again, there is this lookup instruction that's being used in the background to look up the content of the set, and at the same time it will return something, namely this, into a register, and the net instruction will then just grab whatever is in that register and push it into the packet for replacement operations. And that's basically the greatest feature and the most important one, because that's the one feature that allows you to very efficiently replace the rule set. And it's also something that you can't do with IPtables, because now suddenly we have full control over the control flow of the rule set with vertex mapping. So you can say, for this IP source address, accept, for this one, drop, for this one, jump to this chain, jump to that chain, all in a single rule. There is no overhead in doing a linear evaluation as with IPtables. So this is basically, you can represent everything with a tree or a decision tree. For debugging, we now have an equivalent to something for something like the routing monitor that you have with the IP route package. So if you launch NFT in monitor mode, then it will log every rule that is being added. It will log when a rule goes away, and you can just check what's happening on the computer. This is also very useful for tools like FirewallD, because now they can learn when someone else other than them starts to change rules, and it allows them to discover what's happening outside of their control. For debugging, IPtables has a feature called trace. You add a rule with this trace keyword, and then after that you're basically on your own. You have to look at the kernel ring buffer, because it now starts to fill with such crazy output for every packet that is being matched somewhere in your rule set, and it gives you line numbers, and then you have to basically look at the IPtable save output and then somehow map this output that you're getting to your rule set, and then you have to figure out yourself why this matched or didn't match. In nftables, that's integrated natively now. So you also add a trace rule, and after that you no longer have to do anything special. You just fire up the trace monitor mode, and then it will dump directly every rule that is being matched, and not just a line number. You will also see an ID number, so you can figure out if there are two packets that are matching at the same time, you can tell them apart, and you know this packet is going through this rule and this policy, and it matched somewhere in this verdict map, and there was a jump verdict, and that's should allow debugging in a much more simpler way. And it's also internally implemented via Netlink, so you could also subscribe to that automatically in a programmatic fashion and get Netlink parsable data to allow, say, a graphical representation of what packets are being matched. So last slide, so we should be on time. So future work, the one outstanding thing is a high-level library for third-party applications to integrate with. That will happen, unlike with IPtables, where there is no such thing and there will never be such a thing. It's also not yet entirely feature complete, so some of the popular match extensions from IPtables that we don't have at the moment is policy matching for IPsec, rate estimator, reverse path filtering is missing. Hash limit is still missing, but it's being worked on, so that will happen soon. Some targets are missing, for instance, TCP MSS mangling, the contract target is missing. There is no NFQ and contract matching for the bridge family so far. And we also have not yet done any extensive performance testing and optimization work on nftables, although nftables itself should be quite fast, because there are no logs anywhere in the evaluation path, and there are no default counters anymore. So a lot of the performance penalties that IPtables has to pay by design are no longer there anyway. If you want to look at nftables, I highly recommend this nftables wiki, which should have a lot of examples for you to look at. And any questions?
If I have already IPtables installed and working, is this some command where I can say nft pick up these rules and write them?
Yes. So the question was, if you have an IPtables rule set, is that something to translate your rule set to nftables? And the answer is yes. There is a conversion tool being worked on. And it's slowly, as we extend nftables to replace a particular feature that is only available in IPtables, that's being extended to give you the optimum output for,
You showed this phrase feature for matching several IP addresses. Is there, for example, an alias for RFC 1918 for the private addresses?
So the question was, there is this curly brace syntax to match several IP addresses, and the question was whether there is an alias to, for instance, match on RFC 1918 addresses. The answer is no, but nftables does have a define feature. So you could create a define that expands to this list. Basically, we could even add it to the nftables default config file. It would be something to consider, yeah. slides on it? Yes. Okay. Hello. Do you have here next presentation?
Yes.
Yes. Okay, I'm Jiří, and there somewhere is Alex. We are for the session shares for these rooms. We'll help you.
Well, I can.
Yeah.